Hi everybody and welcome to today's lecture. So hopefully you're all here for Year 11 Maths Advanced. So I'll be your lecturer today. My name's Alice and I'll introduce myself a bit more in a little bit. But yeah, I'd like to just say welcome to all of you who are here. For those of you who don't know, these lectures are run by HSC Notes. It's just like a company providing resources for high school students across Australia. So for you guys, you'll be looking at stuff in New South Wales, so they've got heaps of resources for students through the HSC. So I guess just like some of the stuff you can find with ATAR Notes, I'll just quickly run through with you. So there's heaps of study notes available that you can download on their website covering most of the prelim and HSC courses. There's lectures which are like this one that you guys are all watching that are run by past Year 12 students who have done the course before, have done well in the course, so I guess can provide a little bit of like an inside scoop, I guess. On the ATAR Notes page, there's some discussions, which is like Q&As between some Year 12 grads, recent Year 12 grads, and other students as well, just to discuss what you guys are doing, what you're feeling for your exams, for things like English, like different essay questions from different schools and stuff. If any of you guys are interested in that, there's some videos, which some of you guys may have seen before. There's just like another way, I guess, to look at your content. There's a newsletter just to stay in the loop with all things HSC related, an ATAR calculator, which for you guys in Year 11, you probably wouldn't have looked at yet. But for eventually in Year 12, when every Year 12 student gets to that point where they're just really looking to see what marks do I need to get my ATAR, my like goal ATAR, it's there. I mean, if you want to look at it now, go ahead, but most of you probably haven't reached that stage yet. Then you've got just some articles just about like study strategies, study tips, how to get ready for like specific subjects and exams, and then like heaps of other free resources. If you want to check it out, there is a link down here in the bottom left-hand corner. If you want to check out any of this stuff, feel free to have a look on that website and you'll see all of this there. And just some other resources that ATAR Notes does do is TuteSmart, which is just like the tutoring portion of the ATAR Notes company. Again, just from recent Year 12 grads who've done a subject that you're interested in and have done well in it. You can look at TuteSmart for most of your prelim and your HSC subjects. So if you're looking for tutoring, any online tutoring, you can check that out. There's also the study guides that some of you probably have seen before. They come in like little books that are like, each of them have like a different colour and stuff. They are just like notes that go like by each syllabus point, as well as there's some that are topic tests. And you'll also may have seen the study guides for your texts for English. So you can find a study guide for pretty much most of your HSC texts and a lot of your prelim texts as well if you guys need a little bit extra help with your English analysis. And then there's also Ed Unlimited, which is all those study guides in like an online library. And if you get Ed Unlimited, you can look at all those study publications. So yeah, again, if you want to look at any of that, check out the link in the bottom left-hand corner. But otherwise, we will get on with today's lecture. So today, hopefully, again, you're all here for prelim advanced maths. So it's great that all of you guys are here with us. And for those of you watching the recording, hello as well. So yeah, presented by me, I'm Alice. I thought I'd just introduce you guys to myself before I guess, get started with today's lecture. So I graduated in 2022. With an ATAR of 99.3, and I'm currently studying medicine in Newcastle. If any of you guys are interested in studying medicine, I would definitely say Newcastle's the way to go. I'm a little bit biased, but such a good course if any of you guys are interested in that. So yeah, in my HSC year, I only did 10 units. So those are the 10 units I did. You can see them on screen there. In year 11, I actually did quite a different sort of subject scheme. So I did bio, chemistry, economics, English advanced, extension maths, and 1 unit religion. So I did change my subjects a bit from year 11 to year 12. So yeah, I've got a lot of maths background behind me. If any of you guys are interested, I do tutor all these subjects with TutorSmart, and I run our HSC maths class. If you guys want a little bit extra support going into the HSC next year, you can check that out. But yeah, so that's a little bit about me just before we begin. So with today's lecture, we're going to be covering 5 topics. So we'll start with statistical analysis, which is like all your data and things, functions, logs and exponentials, which is probably the biggest part of today's lecture. Then we'll look at calculus, some trig quickly, and then we'll do a little bit of a summary at the end and talk about exam tips and how to approach questions in maths. So through this lecture, there will be a chat function if you guys are watching it live. So feel free to pop any of your questions in that chat and we can reply to them. And yeah, without further ado, we will start with our first topic today, which is statistical analysis. This is quite a big topic as part of the Year 11 course. I use a lot of this in Year 12 as like the basis of your Year 12 statistics. So good thing to have like a good grasp on what it is and how you can apply all these sorts of different things. So we'll start with, I guess, just looking at like what actually is probability. So your probability is just the likelihood that an event occurs. Whenever you're thinking about probability, you're thinking of it either as a decimal, a fraction, or percentage. So your probability will always lie between 0 and 1. If you think of like that as a scale, with 0 being like it's impossible for something to happen. So thinking about like if you've got a 6-sided dice, it's impossible you're going to roll a 7. And then 1 being like it's guaranteed certain something's going to happen. So again with that dice, like the probability of rolling a number between 1 and 6 is going to be definite. So yeah, everything lies between 0 and 1. When you're thinking of probability, you are thinking of like decimals. You're not ever thinking of a whole number. So the possible events within probability are called the sample space. So any possible outcome that you could get for a given like decision you're making or like choice you're making is the sample space. So again, really common example you'll see is dice. So your sample space for your dice is 1, 2, 3, 4, 5, and 6. If you've got a 6-sided dice, or if you're flipping a coin, your sample space is heads or tails. Those are the only 2 options that you can get. And so yeah, with this question, pretty simple question, but just to see that everyone's got a bit of an understanding of what probability is, I give you guys 20 seconds for those of you watching it live if you want to pop an answer to this question in the chat. And for those of you who are recording it, give it a go as well, and we'll just see how we go. Okay, cool. Well, hopefully you guys all got that. The next thing we'll look at is, I guess, the basis for like the mathematical applications of probability. For I guess when you're sort of having to calculate things rather than, when you're thinking about a dice, like the probability of rolling a 1 is 1 in 6. And that's sort of something that for most people, you just sort of know, you don't really have to calculate. But for things that we're more are looking at actually calculating, we can think of the probability of an event, where probability is P, always denoted by P, of an event, E occurring, is given by P of E is equal to the number of favourable outcomes over the total number of possible outcomes. So when we're looking at this E, that will often change depending on what you're trying to find the probability of. You probably wouldn't denote it as E. So like, for example, if we're looking at a dice and we're thinking, okay, what's the probability of rolling a 1? You would typically write P of 1 and replace that E with a 1 because that's the event we're looking at. And then writing it like that just helps whoever's marking your answers or your work really clearly see like what you're trying to find. So when we're looking at the number of favourable outcomes, we're thinking about what outcomes satisfy our event. So With a dice, if we're thinking about probability of rolling a 1, there's only one favourable outcome because only one side of the dice has 1. You'd start to get a little bit more if we're thinking about like what's the probability of rolling an even number, and then all of a sudden you've got 3, you've got 2, 4, and 6. And then the number of possible outcomes is our sample space. So how many outcomes could happen? So again, back with this dice example, you've got 6 possible outcomes. So 6 will become your denominator. And if we're looking at even numbers, 3 would be our numerator. And we get the probability is 1 on 2 once we've simplified 3 on 6 down. So yeah, that's just like the basic formula for looking at probability. This is also super common notation, which is really important that you understand. So P of E is just the probability of an event occurring. And P of E dash is the probability that the event doesn't occur. So it's every possibility but the event not occurring. The event actually occurring. So again, we'll just look at the dice. Super simple example for you guys to understand. But if we're looking at the probability that we roll a 1, our P of E is 1 on 6 because there's one favourable outcome of 6 possible outcomes. And then the probability of not rolling a 1 is 5 on 6 because we've got 5 favourable outcomes, because any other number we roll other than 1 is going to be favourable because we're looking at the probability of not 1 over 6 possible outcomes. Okay. And because we're looking at probability on a scale, the probability that an event occurs and the event not occurring will always equal 1, right? Because in essence, you have to have one of the other. If you're rolling a dice, it either rolls on 1 or it doesn't. And if it rolls on 1, we're here. If it doesn't, we're here. So we know in total our probabilities will equal 1 because it's certain that we'll either get it or we won't. When you start doing some more probability questions and like harder probability questions, I guess, it becomes sometimes a lot easier to find the probability of the complementary event. So to find the probability that something doesn't occur, where this often comes up, which you may have or may not have seen these sorts of questions before. They sort of come up a little bit more in year 12, but it'll be like, Jack has 6 marbles, he's got 2 red and 4 blue. Find the probability that at least 1 blue marble is chosen if he picks out like 3 marbles or something. And when you think of that sort of question, that it becomes a lot easier to find the probability that there is not a blue marble chosen than there is. But don't stress too much about those sorts of questions. They're the sort of thing that you get used to once you start seeing them a little bit more. But yeah, anyway, the next sort of thing that we're going to look at is relative frequency. So the relative frequency of an event is a measure of how many times you actually get the event happening if you perform the experiment repeatedly, which is different from theoretical probability. So your theoretical probability is what you think and what you can predict will occur, like based on like the rules of chance, right? So if we're thinking about flipping a coin, it's theoretically, it's 50-50 that you're going to get heads or tails. Okay, so the theoretical probability of getting a head is 50%. So this is a little bit different from relative frequency, because relative frequency is looking at how many times does it actually occur. So if we flipped a coin 10 times and we end up getting heads 7 out of the 10 times, our relative frequency is 7 out of 10. Like, yes, theoretically we could get heads or tails and it's roughly even. Relative frequency is looking at how many times you actually get it if you perform the experiment. Most of the time when you guys are doing statistics questions in your exams, particularly as you are moving into your HSC year in about a term, your theoretical probability is what you deal with a lot more. And if you are looking at relative frequency, they give it to you in the question. So it's not too tricky to sort of use your relative frequency, as long as you understand that if they say in the question the relative frequency of something, you understand what that means and how that's different from the theoretical probability. but that's how that most commonly will come up for you guys. So then we've also got the probability scale. So like I was saying before, all of our probabilities lie on a scale of 0 to 1, where 0 is something is absolutely impossible and 1 is something that is absolutely certain. Okay, so everything is between this scale. You can't have something that's more than certain and you can't have something that's less than impossible. So really common thing to see when you're looking at 50-50 is heads or tails on a coin. Impossible to roll a 7 on a dice. If you are looking at a regular dice with like 1 to 6 on it. Something that's unlikely, winning the lottery. Not to say that it's impossible, because it's not, because you could win, but it's just not that likely, considering everything that has to go in favour to make that happen. Things that are certain, the sun will rise in the morning, like something like, if I roll a dice, you will get a number that pops up on one of the faces. So yeah, just make sure when you're thinking about probability, you are thinking of things in terms of a scale. Whether that for you find it easier to look at fractions, decimals, percentages are technically on a scale because 100% lies at 1 and 0% is 0. So whatever you find easiest for you to look at, to be able to compare probabilities, do that. You want to make everything as easy as you possibly can for yourself. But yeah, you want to be able to look at this scale and think about where different things lie so you can compare them. Okay, so the next thing we're going to look at is multi-stage events. So the complement of event A is A dash. Okay, so like we were saying, if you see probability with a letter with a dash on the top, all that means is the probability that the event doesn't occur. Okay, so we've been over that a little bit, so I'm not going to focus on that for too long. Then we've got the intersection of two events, A and B, which is denoted as A, this little thing that looks like a rainbow, and B, which is the probability that both events occur. You won't see this too common with like your basic probability questions where it's for like dice, coins, like picking a number sort of thing. You start to see intersection when you've got two events. Okay, so think about if I flip a coin and roll a dice, what's the probability that I get heads and I roll an even number? Okay, so if heads is event A and rolling an even number is event B, the probability that both of those happen is equal to A and B. Okay, so this just pretty much means and. And so that's the intersection. We'll talk about this a little bit later when we look at Venn diagrams, but you will see commonly this notation when you are looking at Venn diagrams, because the probability of A and B is represented by the crossover of the two circles on a Venn diagram. But we'll talk about that a little bit later when we look at them. And then we've got third, the union of two events, A and B, is denoted as A union B, where either event occurs or both of the events occur. Okay, so again, if A is rolling heads and B is an even, getting an even number, the probability of A union B is the probability that A occurs, the probability that B occurs, or the probability that A and B occur. This formula is actually on your formula sheet, so don't stress too much about having to remember it. But this is the formula for finding the union of two events. So we've got the probability of A union B is equal to the probability of A plus the probability of B. And then you do actually minus the probability of A and B, because if we don't minus it, we're going to get double ups. Okay? Because the probability of A occurring already takes into account the times where A and B both occur. And then we've got the probability of B takes into account where B and A occur. So we need to minus A and B so we don't end up with any double ups and get a probability higher than we actually have. Super easy way to check this if you have forgotten to minus, if your probability pops up and it's greater than 1, you've probably forgotten to subtract this from your equation. But yeah, this is on your formula sheet, so don't stress about remembering it, but just important to know and be familiar with how to use it, and to know what each of these 3 terms means. Okay, so then we've got tree diagrams. So for the next little bit, we'll be looking at some visual representations of data. So we've got tree diagrams are used when there are 2 or 3 choices, such as a coin being tossed where the choices are either a head or a tail. You don't want to be doing tree diagrams when you've got like 6 different choices, because otherwise you start getting like really complicated, really messy, crowded diagrams. So you only do it when there are few choices available. But you can do it when there's like lots and lots and lots of steps. So like first step, second step, third step, fourth step. So it doesn't really matter how many steps there are. And I mean, you could use it if there are a lot of choices. It just gets a lot messier when there are choices. So simpler to do when there's only 2 or 3. So we've got this example here, and the tree diagram's already been given to you. So the example is 2 coins are tossed. What is the probability of getting at least 1 head? So I'll give you guys all about 30 seconds or so. If you want to type your answer in the chat, or if you're watching the recording, just give it a go as well. So I'll give you about 30 seconds to do that. Excuse me, sorry. Okay, anyway. Hopefully everyone's given that a go and you've popped your answers in the chat. So yeah, awesome. Okay, so then we've got conditional probability. Now this is probably the part of probability where people get the most confused, and where things start going a bit haywire, when we're thinking about probability. Okay, so we now know how to find the probability of event B occurring. So how do we find the probability that event A has occurred given that event B has already happened? So essentially that's what conditional probability is. It's like, what's the probability of something happening given that something else has already happened? And that's what this little line in the middle of A and B stands for. It's what's the probability of A given B has already happened. This formula, again, is on your formula sheet, so don't stress about remembering it. But what it means is the probability that A has happened given B has already happened equals the probability of A and B occurring, all divided by the probability of B. Okay, and that's how you find the probability of A given B has happened. So like I was saying before, this A and B is represented by our intersection. We've got the probability of B and then the probability of A as well on either side of our circle. Okay, so that's all you really need to know about for conditional probability, is how to use this. This formula actually comes in as well when you're trying, the question might ask you to find the probability of event B. And in the question they'll give you probability of A given B and the probability of A and B, and then ask you to find the probability of B. And a lot of people get sort of stuck on that question because they don't really know where to go from when they've only given you like these 2 pieces of data. But as long as you can remember this formula and remember how to use it, you can use those things and then just like manipulate this expression, move things around to find the probability of B as well. Okay, so just some more terminology about statistics. So you've got two sort of events that commonly come up in questions. So we'll talk about independent events first, so this blue bit. Your independent events are events that occur without being affected by anything else. If you think about like flipping a head on a coin, the probability that you flip a head is the same whether or not you're only flipping a coin, whether you're flipping a coin and rolling a dice, whether you're flipping a coin and picking a number. The probability of flipping that coin doesn't change if you're doing something else with it. So the way that you can work that out if something's independent is if the probability of A given B is equal to the probability of A. So essentially what this is saying is that even though B has already happened, that makes no difference to whether A or not is going to happen or not. Okay. And then we've got mutually exclusive events. So these are events where the occurrence of one event will exclude the occurrence of the other. Okay. So where P of A and B is equal to 0. So like an example for this is if the probability of rolling a 1 on a dice is A, and the probability of rolling a 2 on a dice is B, and you're only rolling the dice once, you can't get A and B, right? So you're not going to get 1 and 2 when you roll the dice if you're only rolling it once. So essentially, with these two terms, it's in the name. Independent events means the events are independent of one another. They don't affect each other. And then again, in the name, mutually exclusive. They're exclusive. If one happens, the other cannot. So if you ever get stuck thinking about what's an independent event and what's a mutually exclusive event, think about it in terms of their names. Okay, so just got a little bit more on statistics before we move on to functions. Our Venn diagrams, super common representation of data, super common thing to come up in terms of questions, or even super common things that sometimes your statistics questions will ask you to draw. So super important to be familiar with them. So our Venn diagrams allow us to see the relationship or overlap between two or more events. Okay, now something that a lot of people miss or forget to do is when you're drawing a Venn diagram in an exam, or even like when you're practicing for exams and stuff, you have to include a box around it for the probability that neither event occurs. Okay, so we've got A dash, which we know is the probability that A doesn't occur, and B dash, which is going to be the probability that B doesn't occur. And we've got A and B, so this is just the probability that neither event A nor event B is going to happen. Okay, so even if it's 0 on the outside, even if it's guaranteed that either A or B or A and B will occur, you do need to include this box on the outside and write 0 somewhere in that box. Okay, same thing if you've got more than two events. Again, this is the probability that A does not occur and B does not occur and C does not occur. Okay, just want to make it super clear that you understand that nothing will happen outside of this range, or that there are things that are going to happen that aren't A, B, or C. Okay, so with your Venn diagrams, most of you would have seen Venn diagrams before. So we'll just quickly look over this. So this probability that A occurs, probability that B occurs, A and B, where the two circles intersect. Pretty simple. Same thing if you've got more than two circles. Where there's no crossover, it's just A, just B, or just C. Between the crossover of two circles, you've got the probability of two events occurring, and where all three circles overlap, you've got the probability that all three events occur. You could theoretically have Venn diagrams that have, 5, 6, 7 circles. They'd be super hard to draw, and you guys will never have to draw them. You probably wouldn't get a Venn diagram with more than 3 circles, so don't stress, but just be super familiar with what each of the intersections between the circles mean. Okay, so just a little bit more in the Venn diagrams. Union of A or B is all of it, because we know that union means A or B or both. We've already talked about A and B is just that part in the middle where the 2 circles intersect. The probability of not A, so the complement of A or A dash, depending on how it's given to you in the question, is everything but the A circle. The probability of A is just A and not B, so you don't want to think about that part in the middle. And then if we've got mutually exclusive events, it's neither. You're going to have nothing shaded. Okay, so I'll just give you like a little bit more time just to read through that if you need it. Okay, and then the last little bit of statistics that we're going to look at today is what these 2 terms mean. And if you can take away anything from statistics today, take away this bit here, because for most people, this is probably where you will go wrong when you're doing your statistics questions, particularly in year 11 when they're not too tricky just yet. So in the question, if it says and, it means multiply. If it says or, you want to add your probabilities. Okay. So if you want to have the probability of getting 2 heads over 2 tosses, so think of that as heads and heads, you want to multiply. If you want to get a head or a tail on the first toss, you want to add them. Okay, so if you're running notes or anything, if you're going to take anything away, please take this away. It'll make your life so much easier when you start to do more probability questions. And it'll be super good for you guys in year 12 if you can already get a grasp on what this means. So and is multiply, or means add. Okay, so multiply your probabilities or add your probabilities. This rule obviously is for like multi-stage events, so you'd only do this if like you've got 2 events occurring. Because otherwise, if you only have a single stage event, you only have 1 probability, so you can't multiply or add anything. But yeah, please just take this away and you'll be so set for statistics. Okay, so that is statistics all done for today's lecture. If you guys do have any lingering questions, feel free to chuck them in the chat. But otherwise, we're going to move on to functions. Functions is kind of a big topic in year 11. There's like a lot of content, I guess. And it's super important to get a good grasp on this now because you do so much with functions in year 12. And a lot of it you don't go over again in year 12, but you're just sort of expected to like have remembered it and to remember how to do it. So super important if you guys get a good grasp on it now. So our functions essentially are just equations or graphs where there's only one y value for every x value. So there are lots of types of functions, such as these ones. Some of them have discontinuities, which means they're not just one straight line. So if you look at this graph of the reciprocal, there is a discontinuity. You probably can't see it because this is fairly zoomed out, but if you zoomed in enough, you would see that there is nothing that actually hits the y-axis. So if we look at this graph here, the linear graph, you can see each of these x values only has one y value. Okay, same thing with this quadratic. Each x value only has one y value. Now, some people start to get a little bit confused when you're looking at quadratics. It is okay if one y value fits more than one x value, as long as each x value only has one y. Okay, so if you look at this here, 1 and -1 both hit the same y value, but 1 only has one y value and -1 only has one y value. So that's why this is still a function. Okay. Same thing with the absolute value. You'll see that there's, two x values that hit each y value. That's completely fine as long as each x value only has one y value. Doesn't matter how many x values each y has. Okay, so that's a little bit confusing to think about, but bear with me. Same thing, square root function, each x value's only got one y. Our cubic, each x value's only got one y value, and same thing that we've discussed about our graph of the reciprocal as well. So yeah, with these functions, we can test for how things, or whether a graph is a function. And the way we do that is through the vertical line test. So this is the test you use anytime you want to test whether a graph is or is not a function. When you draw a straight line down a graph at any point, so at any and every single point on this graph, that graph will only intersect your straight line once. Okay, so essentially what that's saying is that if we've drawn our vertical line through x equals 1 here, if it only hits the graph once, then there can only be one y value. And no matter where we draw that straight line along this graph, it will only ever intersect it once. So we can say, yep, this graph is a function. You guys might not have seen this yet, but this is what your graphs of your sine, your trigonometric function sine looks like. So spoiler alert, that's a function. And then you've got graphs of your circles, which you can see at any point. If you drew that straight line at any point on this graph, it would hit it twice. Okay, because each x value has two y values. And so then we can say for this one, it's not a function. Okay, so just let you look at that for a second. Okay, so probably the most important thing to take away from functions in year 11 is looking at the domain and range and working out how to calculate, I guess calculate is not the right word, but figure out your domain and range. So super duper important. So when we're looking at the domain is the x values for which a function is defined. So essentially, where on the x-axis will our graph exist? Then we've got the range, which is the y values for which a function is defined. So essentially, where on the y-axis is our function going to exist? Okay. So, for example, if we're looking at find the domain and range of y equals x squared, you'll look at your parabola, we've graphed it here for you, and you'll see that this graph slowly trends outwards. So if we've put no limit on that, it can hit any x value, right? Because it'll just keep getting wider and wider and wider and wider. The higher it goes up the y-axis. So we can say for this that the graph can take any real value for x. And so then you can write that as the domain equals all real x. Okay, because at any x point, we can generate a y value. There's not a single value, a real value for x that you can sub into this equation that wouldn't give you a y value. Okay, then when we've got range, we can see, when we're just looking at this graph, that our graph is going upwards only. Okay, it's not going down, and we can see that it starts at y equals 0. So we can say that our graph is going up and up and up and up and up, and there's nothing that's going to stop it going up. But we're not going to have any value below 0 for y. So then we can say that our range is y is greater than or equal to 0. Okay, so that's that for domain and range. Super important that you understand how to work this out. Super easiest probably way to do it is to graph and to actually look at the graph. And then from there, it's super easy to look at, okay, where does it exist for x? Where does it exist for y? Okay, so also important to understand even functions and odd functions, which we'll look at in a second. But our even functions are functions that are symmetrical about the y-axis. Okay, so essentially that's saying like the left and the right are the exact same of the, thinking of like left of the y-axis and on the right of the y-axis. So their line of symmetry or reflection, depending on how you want to think about it, is about the y-axis. Okay, so for example, you can see this in a semicircle. It's the exact same on the left and the right. And then you can see it in the parabolas as well. The exact same on the left and the right. Now, a question type that you guys might get given is to prove that a function is even. If you ever get asked to do that, the only way to prove a function is even is to show that f of x is equal to f of negative x. So essentially what that's saying is if we put negative x into our function, so let's look at this one for the parabola here, we would get the exact same value as if we put in just x. Okay, so if we're thinking about this, when y is equal to x squared, we get, y is equal to x squared. But if we put in negative x and we got y is equal to negative x in brackets squared, negative x squared and x squared are equal to the exact same thing because that squared will cancel out our negatives. So for both f of x and f of negative x, we're going to get y is equal to x squared. Okay, and that's how we can prove that our functions are even. Okay, and then the converse of that is looking at odd functions. So our odd functions are functions that have symmetry about the origin. So it's like if we spun this around the origin, we could eventually get back to this exact same graph if we just spin this up and round, so that this point now hits up here. So when the graph is rotated 180 degrees about the origin, you'll get the original graph again. So this is seen in cubics and in hyperbolas. So you've got your hyperbola here and your cubic here. If you guys haven't seen these graphs before, that's what they are. And just like when we had the even function, we can also use a little formula to prove that we've got an odd function. So the way that we do that is by showing that f of x is equal to negative f of negative x. Okay, so if we've got fx equals x cubed, then it's an odd function if negative x cubed gives us the same thing as f of x, which for the cubic it does. Okay, so that negative f just means the whole thing, our whole function is negative, and then the negative x says that the x within our function is also going to be negative. And if you can prove that f of x is equal to negative f of negative x, then you've got yourself an odd function. And the only way to prove that a function is odd is to prove this. Okay. So another super important thing that you guys want to be able to make sure you can do, at least by the end of year 11, is to solve a quadratic. So there are 3 methods that you guys can use to solve your quadratics. You've got factorization, which is when you make your function equal to 0, you find the factors that go into it, and then you solve each bracket for equaling 0, and you get there. You can complete the square, which I'll be super honest with you guys, in the HSC you probably wouldn't be looking at doing just because it does tend to take up a lot more time, and a lot more like working and thought, like just a lot more brain power than doing factorization or completing the square. But if it works for you, it works for you, and you can do it. I mean, it does get tricky with some questions, and yeah, things just get a little bit harder when you're doing this, but essentially just making both sides be able to get square rooted, and then you just solve from there. And then you've also got your quadratic equation, which I'm pretty sure is on your formula sheet, so don't even worry about remembering it. Your quadratic equation is super good, and when I was doing my exams, it was always my go-to, unless the question said to factorize or complete the square, just because it's a little bit foolproof. When you're looking at factorization and completing the square, there's a lot of, I guess, like guessing and checking that goes into that to making sure that these things sort of work. Whereas this is like a formula that you can honestly just put in your calculator and it'll give you your answers. With this, I guess what a lot of people forget is that you do have to check for plus and minus, which you can't put plus and minus into your calculator at the same time. So you do have to remember to check them to get both answers. But yeah, I would honestly say quickest way to do it is your quadratic equation, then followed by factorization, and then completing the square. So yeah, that's how you solve your quadratics. And essentially when you're solving your quadratics, you're solving for the x-intercepts. A lot of the time, when you get given these in your exam, you are just solving it to solve them. But the application of solving your quadratic is to solve for the x-intercepts of a parabola. Okay, so I'm just going to leave this there for like 20 seconds, just so you guys can look through each of the different methods of doing it. Okay, so then we've got the discriminant is the last sort of bit of functions that we're going to be looking at today. So when you're looking at your quadratic formula, you've got ax squared plus bx plus c equals 0. When you solve this using the quadratic equation, the part you put inside the square root is called the discriminant. Okay, and your discriminant is symbolized by this little triangle, which is the Greek symbol for delta, as part of the Greek alphabet. So essentially, your discriminant or delta is equal to b squared minus 4 times a times c, which again is just what exists underneath the square root sign of your quadratic equation. So the discriminant will tell you if the roots of the quadratic equation exist, and it'll tell you about the nature of the x-intercepts. Now, the reason that this occurs is because if whatever this is equal to, if it's less than 0, you're going to get a negative number, and you can't have a negative number underneath the square root sign. So essentially that's saying that there are no x-intercepts, like there's no points where x will your graph will intercept the x-axis. So essentially no x-intercepts. If it's greater than 0, then you will get x-intercepts. And then if it's equal to 0, you'll get x-intercepts as well. But we'll look at what the difference is between those two in a second. So for when your delta or your discriminant is equal to 0, there is only one solution to your graph. So there's only one x-intercept because both of your roots are going to be equal. Now, when you think of this, it's because when we're looking at our quadratic equation, we've got negative b squared plus or minus the square root of b squared minus 4 times a times c. Sorry, it's not negative b squared at the beginning, just negative b. So essentially, if we've got 0, it's going to make no difference whether we're plussing or minusing it, because plus 0 minus 0, same thing. So we're only going to get one solution to our graph. That solution is going to be real and rational. And so as a result, you'll see that your parabola will only touch the x-axis in one place. Okay, so that's what it looks like if you've got discriminant that is equal to 0. So then the difference is when you've got discriminant or delta that's greater than 0, you're going to have two solutions for your quadratic equation. So again, if you're thinking of this in terms of your quadratic formula, you're going to have plus and minus, and it's going to make a difference whether you plus or you minus whatever your discriminant is. And that's how you end up with two solutions. Your solutions will be real, and they may be rational or irrational. So you may end up with, like lovely x-intercepts of like 1 and minus 1, but you could also end up with like, the square root of 3 and the square root of like 2. So they could be rational or irrational. Your parabola is going to touch the x-axis twice because you're going to have two solutions, which means two x-intercepts. Because like we were saying before, when you are solving using the quadratic formula, you're solving for x-intercepts. And then this is what you call an indefinite function, because the value of x could be positive or could be negative. You could have two positive x-intercepts, you could have two negative x-intercepts, one negative, one positive. Just means if your discriminant is greater than 0 that you're going to have two solutions. And then finally, if 0 is greater than delta or greater than your discriminant, you're going to have no solutions to your quadratic equation. These are what you call non-real roots. So there's no solution to the quadratic equation, and you can't have the square root of a negative number. You can't, like in real terms, you can't have the square root of a negative number. So when you're looking at this, you're going to have no x-intercepts, because no solutions means no x-intercepts. Okay, so graphs that look something like this, or, maybe they'll sit like here and just never touch the x-axis. You never really know. So, that's how you use your discriminant. Important to know how to use, important to know what it means. The discriminant comes up a lot in application of other questions. Just super important to know what it means to have a discriminant that's equal to 0, a discriminant greater than 0, and a discriminant less than 0. And then to also understand by looking at a graph what the discriminant will equal. Okay, so looking at a graph, if you only see it touch the x-axis once, you can immediately know, okay, the discriminant is going to be 0. If you're looking at a graph and there's two x-intercepts, immediately you can recognize, okay, the discriminant is going to be greater than 0. And then if you're looking at a graph and there's a discriminant less than 0, immediately you can recognize, okay, the discriminant is less than 0. Sorry, I worded that the wrong way around. But yeah, that's essentially the key points of functions that we're going to look at today. So the next bit that we're going to look at is probably like the biggest bit of this lecture. So we're looking at logs and exponentials. These come up a lot, and you do a lot with them in Year 12 as well. So it's super important to understand what they mean. And to know how to use them, know how to use log laws, know what their graphs look like, know how to differentiate them. Eventually next year, you'll look at integrating them, but that's a problem for another time, so don't stress about that now. So, I'm not going to spend too much time looking at these, because hopefully you are pretty good with your index laws. So essentially, ax times ay, if there's the same base, you can just add your indices. If there's the same base and you're dividing, you can minus them. If you've got an indice to the power of something, multiply them. A to the negative of an indice, 1 over a to it. Hopefully you know this is how we generate these, and then the power of 0 to anything is 1. Okay, so I'm just going to leave this on the screen for 2 seconds just so you guys can have a look. Okay, so hopefully looking at those has rung some bells for you guys, because we will come back to, I guess, these laws again, sort of. You'll see what I mean, but anyway. Okay, a log. A logarithm is just another way of expressing an index or a power. So this is like your general form of how you can change indices to powers. So if you're looking at 4 cubed is equal to 64, that's the exact same as saying that the log of 4, so the log of this base, 64, whatever it is equal to 3. So it's just, I guess, a way of expressing your indice as the subject of an equation. So in other words, log b of x is equal to whatever number can be used to raise b to equal x. Okay, so if you guys want to jot anything down from logs and exponentials, this is it. This is the formula. If you guys can remember that x is always going to be your subject when you're changing from an exponential to a log, you'll be set to go. And just like when you've got your indices, the base must be positive, so your b will always be greater than 0. If you ever are like trying to work out a question and you all of a sudden get a negative base, you have done something wrong and you must go back and check where things went wrong. So yeah, this is just the main takeaway from this slide. You don't get given this on your formula sheet, so you do have to know it yourself, and it comes up a lot, so trust me when I say please write this down. So yeah, your logs are just another way of expressing your indexes as the subject. So another way to think about your logs is to think about them as the inverse of having an exponential. So just like if you've got addition, the opposite of addition is subtraction, the opposite of multiplication is division. You guys haven't quite done integration yet, but if you know what it means, you'll understand this. If you don't know what it means, don't worry. But differentiation is the opposite of integration. And in the same sense, your exponent has an opposite, which is a log. Okay, so these two are just the opposites of each other. Okay, so if you guys want to have a go at some of these questions, or maybe give you like a minute or two, if you want to have a go at a couple of them, just pop your answers in the chat and just make sure you specify which question you've done. If you want to see if you've gotten them right, I'll give you maybe like 2 or so minutes just to see how you go with changing these into exponentials and then evaluating them. Okay, well, hopefully I all gave those a go. Cool. So the next thing we're going to look about is logarithmic functions and what the graph of your log will look like. So any function that follows this basic form, y equals log a to the x, is a logarithmic function. And this in general is what your log functions look like without like translations, transformations, things like that. So in general, these functions have a domain where x is greater than 0. They will never touch the y-axis itself, but they will approach it and get really close to it, just never touching it. And then as you can see, all our x values will be positive. All real y values are positive because this will just keep going down and down and down and down. And this will just keep going up, 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 up. And then you do have an asymptote that as y is approaching negative infinity, x will approach 0. But like we said, x will never touch it. And you'll notice that if you have ever looked at the graph of an exponential, which sort of sits like here, that it is just the opposite graph, because like we were saying before, our logs are the opposite of our exponentials. So it is just the opposite graph. And so in general, this is what our log functions look like and what their domain, range, and asymptotes are. And then here, in case you haven't seen the exponential function, this is what it looks like. So any function with the form y equals a of x is an exponential function. So just like our log function, we do have all real x, not like our exponential function, I got a little confused there. But we do for this one have all real x. So this will keep going down and down and down and down, and this will go up and up and up and up until it keeps going wider and hits all the x values. And then like the log, we've flipped our domain and range essentially. And so now our range is y greater than 0. Whereas with the log, it's our domain that's x greater than 0. So you'll see that this will go down and down and down and will approach the x-axis, but will never touch it. But it can keep going up and up and up and hit every single y value greater than 0. And then we've got, again, the opposite asymptote. So as y approaches 0, so as this keeps going down and down and down, x will approach infinity, but will never actually hit it. Okay, and you'll see the x-intercept there of 1. The y-intercept of 1. Okay, and then you'll see in this one, the of our log function, the x-intercept of 1. So we really are just flipping them and creating the opposite functions. Okay, so that's what our two graphs look like. Important you can recognize them and draw them and, recognize the domain, range, and asymptotes of these graphs. But yeah. So just as we've got the index laws, we also have some log laws. So our index laws parallel the log laws. So they sort of, I guess, are the opposites, just like everything with your indexes and your logs. So when we've got the index law, a to the power of x times a to the power of y equals a x plus y. In this one, if we've got log a of x plus log a of y, it equals log a x times y. Okay, so like in this one, we've got the multiplication on the left and addition on the right. With our log laws, we've got the addition on the right, the multiplication on the left. Sorry, I got that the wrong way around. The addition on the left, the log laws on the right. The multiplication on the right. Sorry, this is just not my thing right about now. Okay, so log a of x plus log a of y equals log a xy. Again, just like you have to have the same base when you're looking at your index laws, you need to have the same base when you're looking at your log laws. Otherwise, you can't do like these things unless we've got the same base. Okay, when we've got the index law, a to the power of x divided by a to the power of y equals ax minus y. Again, opposite sort of thing. Log a to the x minus log a to the y is equal to log a, x divided by y. So again, we've got our same base, and we're flipping the side that subtraction is on, and flipping the side the division is on. And then our third super common log law is log a x to the power of b is equal to b log ax. So that's paralleling the index law, a to the power of x times to the power of b is equal to axb. Okay, so I'm just going to give you guys maybe like 30 seconds to write these down if you haven't already, because these are super, super important. Especially this right-hand side, super important for your exams. Okay, well, hopefully all of you guys have written these down. If you haven't, you can always go back to the recording and pause it, or these slides are available to you guys, so don't stress. But I'm going to give you maybe like a minute or so if you want to have a go at any of these questions, and just put your answers in the chat if you want to see if they're right, and just make sure you specify which question you're doing. But I'll give you guys about a minute to have a go at least one of these. Okay, so hopefully all of you guys have given those a go in the chat. We'll do some more examples now. Again, I'll give you guys about a minute or so if you want to have a go at either A or B, and just pop your answer in the chat to see if you are right when you finished. Okay, well, hopefully all of you guys gave those a go. So just a few more log laws down the bottom here. These ones aren't, I guess, as common, but it's still important to know. So we've got the exponential law, x to the minus a is equal to 1 on x a. And I guess the log law that parallels that one is that log of x to the power of 1 over x to the a is just equal to negative a. And then just as you've got x to the 0 equals 1, log x to the power of 1 is equal to 0. Okay, so I'll just give you maybe like 20 seconds to write those two more log laws down. Okay, so the next bit of looking at logs and exponentials is to look at the change of base law. So essentially when we are looking at a log, if you look in your calculator, there's only 2 logs that you can actually calculate. So there's log e, which on most of your calculators will come up as ln, like the button will be ln, and then we've also got, sorry, I'm just turning the brightness of my computer up. Then we've also got log 10, base 10, on the calculator. So those are actually only 2 logs that you can calculate. So if you get given log with a base of something other than e or 10, you need to be able to find a way to change that log so you can actually calculate it and get an answer. So this comes up super commonly when you guys get questions on logs. You'll have to do like a little bit of manipulation, find a log, and then it'll ask you to calculate it or compute it. And so in order to do that, we have this thing called the change of base law. So essentially what you can do is if you've got log b, where b is anything but e or 10, and we'll come to e in a second, what it means to have log e. But essentially what you want to do is you can change that to log x to the power of whatever your a is, all over log x to the power of whatever your b is. Okay, and then you make x either e or 10. As long as you make both x's on the top and the bottom the exact same, it doesn't matter whether you do e or 10. It'll give you the exact same answer. But just so you can put it in your calculator, this is how you change the base of your logs. Okay. So I'll just give you guys maybe like 10 seconds to copy that down if you haven't already, because it's super important to know how to use this formula. Okay, so we're just going to do some questions with this. Again, pop your answers to these in the chat. I'll give you guys about a minute or so to see if you can do, probably with these ones, you could probably do all 3 in the next minute. Yeah, so give them a go, pop your answers in the chat to see if you're right or not. Okay, so hopefully you guys have all given those a go in the chat. Okay, so like I said, we will talk about log e. So log e is what we call the natural log. It has the notation, you can either write it as log e of x or ln x. This is what that graph looks like. Same as your basic log graph, but we'll talk a little bit about this in a second. Okay, so when we're looking at exponential functions, it gets really tricky and just gets a little bit nasty to do your calculus with lots of your exponentials, just because there's like a lot going on. So basically what you can see happening is that we're looking at the derivative of an exponential multiplied by itself, the derivative of an exponential is itself multiplied by some constant of proportionality. Okay, so the derivative of our exponential here is being still multiplied by our constant of proportionality, which is this red bit. Okay, and so if you look like pretty rough checking, you make your h super small, you can find that between when the limit is h approaching 0, 2 to the power of h minus 1 on h equals 0.69, if we're making this h pretty small. If you do the same thing with your 3, so we make a equal 3, as h approaches 0, 3h minus 1 over h is equal to 1.10 when our h is equal to 0.00001. So essentially we use this small number to show as h approaches 0. So in these two examples above, you can see your proportionality constants are produced for the derivatives of 2x and 3x. Okay, so I'm going to leave you guys to think about this for a second. If you think about it, there must be a number which produces a constant of 1, so its derivative will be the original function, right? Like if you think about it, does that exist? Will there be a number which will produce a constant of 1, so its derivative will just be the original function? Okay, let's just all think about that. Let's ponder. So, funnily enough, surprisingly, yes. So somewhere between a equals 2 and a equals 3, there is a number which makes e to the power of h minus 1 over h equal 1. And so this number is called Euler's number. That's how you pronounce this word, it's Euler. And it's denoted by the letter E, where E is equal to 2.7182818288, it goes on and on and on. It's like pi, that number never actually ends. You could do it to like a million bazillion digits. And so essentially E is just the number which will make the derivative of this 1. Okay. So you guys don't actually have to know like what E is. You can find the value of E on all of your calculators. E is usually denoted as one like above one of your buttons. It's not a button itself. So it's usually you have to press alpha, I think, to get to E on most calculators. On some calculators it'll be shift something, but yeah, you do get E on your calculator. So don't stress about actually remembering what E is. If you can remember that it's like 2.7 something, you're on the right track, and that's pretty much all you need to do. So then we've got the natural exponential function, which is the exponential function with e as its base. So you've got y equals e to the x, and that's the natural exponential. Okay, and with the natural exponential, it shares all the properties of what you call like a normal exponential function. And you use it for calculus because e to the x is the derivative of e to the x is e to the x, because our constant of proportionality with e means that this constant will become 1, so it just becomes e to the x times 1, which is equal to e to the x. Okay, so super important that you guys understand that e to the x, the derivative of e to the x is e to the x. Okay, that's a super important differential principle to be aware of. Okay, so I'll give you guys a second to write this down if you haven't already. Okay, so this is just the simplified version of what we just said. The derivative of e to the x is just e to the x, and that's why it's pretty special. It's why we call it the natural exponential. So yeah, that's just like a simplified version of saying that. So more generally, when you're looking at the exponential function, pretty uncommon you'd see just e to the x. You'd usually see e f of x, where f of x is a function of some kind. So you might get like 2x, 2x plus 1, 3x squared plus 2x plus 7. That f of x can be anything. So the general principle or formula for the derivative of e to the f of x is equal to f dash x times e to the f of x. Okay, so this bit doesn't change. You're just multiplying it by the derivative of this f of x. So your power remains unchanged and your derivative will go out the front. So essentially why that works with just e to the x is because you're doing e to the x, this doesn't change, you're multiplying it by the derivative of your function, derivative of x is just 1, and so then you get e to the x times 1 is equal to e to the x. Okay, so I'll give you guys maybe like 20 seconds just to write that down. Super important that you know how to use this. Okay, so just some examples for you guys to have a go at. Again, pop your answers in the chat, see how you go. And yeah, I'll give you guys maybe like a minute or so to see if you can give at least one of these a go. Okay, so hopefully all of you guys have given at least one of these a go in the chat. Another example, I'll give you maybe like a minute or so, just have a go at this one as well. If you don't get it done in time, no stress, but if you do get it done, again, just check your answer in the chat to get it checked. Okay, well, hopefully you guys have at least started this question, or sort of know where you'd go with it. If you can put whatever you're up to in the chat, if you want to get something checked, feel free to do that. Otherwise, we've got another example for you guys. Don't worry about part B. Do part B after this lecture finishes. But if you guys want to have a go, maybe at part A, I'll give you guys another minute, just see where you get up to, and then we can go from there. Okay, well hopefully everyone's given or at least started this question. If you guys want to put whatever you're up to in the chat, if you want to get something checked, feel free to do that. Otherwise we will just move on. So then we know that the natural exponential has a base e and looks something like this. We've got e to the x or e to the f of x. And so essentially that means that e also is a good base to have when having your logs. So you've got the natural logarithm, log e to the, x, which is equal to ln x as well. So this log e is the same thing as ln. And yeah, as long as you guys know this and this, that's all you really need to take away from this slide. Okay, so when we have a log that looks like this, so you've got log 2 to the 2, that's equal to 1. What you're basically saying is that 2 to the power of what will equal 2. Okay, and of course that's equal to 1. So essentially you've got the same thing when you've got a natural log, e to the e. So e to the power of what is going to give us e. And again, same thing, it's 1. So then you can use this rule as kind of like another log law to manipulate, simplify, or solve logarithms. So anytime you've got the same base as you've got here, the answer will always equal 1. So, log 3 to the 3 is equal to 1. Log 27 to 27 is equal to 1. Anything like that, you're always going to get 1 because we're just saying what, like our base to the power of what is going to give us our base again. Okay, so last slide for logs, just some quick more examples. I'll give you maybe like 30 seconds to have a go at least one of these. And then we're going to be moving on to calculus. Okay, well hopefully all of you guys have chucked something in the chat to get it looked at and to see if you're right. But we are going to move on to our second last topic for today, which is calculus. Calculus is probably one of the most important things you can remember from year 11 for year 12. Like, honestly, probably 60% of the year 12 course is calculus. So super important to know what's going on here. And calculus is kind of like a good topic in the sense that if you know how to approach each of your questions, it's super easy to get those questions right every single time, because there's one approach for each question type that will work. So the sort of questions that if you do enough practice on, you can guarantee those marks in your exam. Okay, so I guess we're starting with just an introduction to differentiation. So the gradient of your function is equal to the gradient of the tangent at the point of contact. I'm just going to quickly do this, just so you guys can see a graph. So the gradient at this point is just equal to the gradient of the tangent at that point. Okay, so one way you can do this is by looking at the first principles. With the first principles, I wouldn't stress too much about actually memorizing this formula. Typically, if any question is to come up with first principles, you will get given the formula at the beginning of the question. So I wouldn't stress too much about remembering it. And if you ever get into an exam and you don't get given this formula, but you know, but you have to use it. The question specifies you have to do it by first principles. An easy way to check, or I guess to sort of like start guessing, is to remember that you have to have H, and that if you can work out what the differentiation of the question is beforehand, then you can sort of start guessing of how you can end up at that answer using your first principles. So yeah, hopefully you guys are familiar with your differentiation by first principles. Your other common differentiation rules are here. These rules are on your formula sheet, so you don't really have to stress about remembering them. You sort of have to remember about how to use them. So your differentiation of C is always equal to 0. To differentiate x to n, it's equal to n x n minus 1. To differentiate two functions that are being multiplied together, it's equal to f dash x times f of x, times g of x plus f of x times g dash x. Your quotient rule, if you're looking at two functions being divided by one another, g of x, or this one, your quotient rule, super important that you get these terms the right way around, okay? When you're looking at your product rule, doesn't really matter whether you do f dash x first or g dash x first. With your quotient rule, it does. It really does matter which way you do this. Okay, so you have to remember to put your denominator as the first term, and then your numerator differentiated minus your numerator times your denominator differentiated, all over your denominator squared. Okay, super important that you get this the right way around, because otherwise you're going to get the wrong answer. And then you've just got the chain rule as well. Okay, so don't stress about remembering these. They're on your formula sheet. Just know how you're meant to use them, what each of them means. And yeah, I guess that's all you really need to know about them. Yeah, just be familiar with them, I guess. Do lots and lots of practice questions using all of these different rules, and you will be absolutely set for your differentiation. So I guess the first application you do of differentiation is in year 11. And essentially you use differentiation to allow you to solve the gradients of a curve at certain points and to find the maximum and the minimum points, as well as find where the curve is stationary, where it's increasing, where it's decreasing. And then you can use that to apply to real life problems. This application to real life problems comes in a lot more in year 12. So if you can become super familiar with how to find them, you'll be super set in year 12 and you learn about the application of them through optimization. You guys wouldn't have heard the term optimization before, and that's fine because you don't need it until year 12. So essentially, the important principles to look at with differentiation is if f dash x is greater than 0, then our curve is increasing at a point. So we can see it here, f dash x greater than 0 at any of these points, and f dash x will be greater than 0 at any of these points, which means our curve is increasing, which essentially, if our curve is increasing, we've just got positive gradients. Okay? Opposite is true for if the curve is decreasing, f dash x will be less than 0, so you can see that at all the points where we've got a negative gradient. And then at the points where our curve is stationary, f dash x is equal to 0. So we can see that at our maximum here, and then our minimum as well. So you want to be remembering these things in blue. They are super duper important. So make sure you've got them written down somewhere, or that you've got them memorized or something. If for whatever reason you forget, increasing means positive gradient. I feel like that's pretty, like those two words, like increasing and positive are linked. Decreasing, negative gradient. Stationary is flat. The tangent at that point would be flat. Okay, so I guess the last little bit of calculus we're actually going to be looking at today is how to find the equation of the tangent or the normal. So these are a really standard question type, really, really common. They get asked all the time. And this is one of those calculus questions that they have the exact same structure every single time. So if you can follow this structure, you'll get these questions right every time. They do come up again in year 12, like you do get these exact same question types again. So if you can get really good at answering them now, you'll be doing yourself a mad favor for next year. So first step is to differentiate, find the differential of f of x, if it's f of x or g of x, a of x, whatever they give it to you as. So then in the question, they'll give you some coordinates. You want to substitute the x coordinate into the derivative you found to find the gradient at that point. Okay, once you've found the gradient, the next thing you want to do is to substitute that x coordinate that they've given you in the question back into your original function, not your differential, but your original function to find the y coordinate. That's only if they haven't given you the y coordinate. Sometimes they'll be nice and you'll get given like actual coordinates, you'll get x and y. But if they haven't been so nice, you want to put the x coordinate they've given you back to the original function to find a y coordinate. And then all you need to do is use the point gradient formula to obtain the equation of the line. So if you guys don't know what the point gradient formula is, it's the formula where you do y minus y1 equals m in brackets x minus x1, close the bracket. So you've got y minus y1, which is the y coordinate you found, equals m, which is the gradient we found, x minus the x value we found that gradient at. Then obviously if you're finding the value of the normal, you use the reciprocal of your gradient. And then you can use the same x and y coordinates. And yeah, that is how we find the equation of the tangent or the equation of the normal. Like I was saying, these are super common question types, so get super familiar with this. If you guys want to write this table down, take a screenshot of it, take a photo of it or anything, I would definitely recommend doing that because these are super common. And if you can nail how to answer them now, you're guaranteeing yourself like 3 or 4 marks, at least in your exam. Okay, because these questions, when you get them, are usually worth a fair few marks. You usually get 1 mark for finding the differential, 1 mark for finding the gradient, and 1 mark for finding the value of the line. If they haven't given you the y coordinate, you might get a mark as well for being able to find the y coordinate. So I can almost guarantee that something like this is going to come up in every single one of your calculus exams. So that's a guaranteed 3 or 4 marks at the very least. Okay, so then now we're moving on to our last topic for today, which is trig. Trig is probably one of my favorite topics. I don't know, I feel like it's good in that there's just a bunch of rules, and as long as you know the rules, you can answer the questions. Most of these rules also are in your formula sheet, so you don't even really have to worry about remembering them. You just have to know how to use them. Okay, so hopefully all of you guys have seen these before and you're familiar with your reciprocal trig functions. So you've got cosec, which is 1 on sine theta, which is just the reciprocal of sine, which becomes the hypotenuse over the opposite. Then we've got sec theta, which is equal to 1 over cos theta, which again, reciprocal of cos, which is going to become the hypotenuse on the adjacent. Then you've got cot theta, which is equal to 1 on tan theta, which is equal to the opposite over the adjacent, which is also equal to cos theta on sine theta. Okay, super important that you guys have these down. And you can quickly remember that cosec is equal to sine, sec is equal to cos, and cot is equal to tan, or the reciprocals of these trig functions. This also super important for when you get those questions that are prove that some really random trig identity is equal to some other random trig thing. This is a super common thing that that you'll need as one of your steps to get to the proof, because a lot of people forget that this exists. And likewise, you've got tan theta will equal sine theta on cos theta. Okay, so then just in case you've forgotten, these are your basic trig identities. You've got sine theta, which is opposite over hypotenuse, so your so, You've got cos theta, which is adjacent of the hypotenuse, which is ka, and then tan theta, which is opposite of adjacent, which is toa, and yet SOHCAHTOA. Like I said, tan theta again is just equal to sine theta on cos theta. And I guess that's really all there is to that. Hopefully you guys remember it. So another super important thing to remember is that cos squared theta plus sine squared theta is equal to 1. This is on your formula sheet. It is unlikely that you'll get actually asked to prove it, but I guess like it's in the scope of the syllabus for them to ask you to prove it. So you should know how to do it. Super uncommon, but if you have the time to learn the proof, it's a good thing to do. So from this equation, you can then derive like 1 plus tan squared theta is equal to sec squared theta, 1 plus cos squared theta is equal to cosec squared theta. These are not on your formula sheet. So if you want to remember them, you've got two options. You either memorize them or you learn how to prove from this that you can get these. Again, the other super common thing you can do with this is then you can get like sine squared theta is equal to 1 plus cos squared theta. Same thing, cos squared theta is equal to 1 minus sine squared theta. So yeah, just knowing how to manipulate this to get all these little bits and bots is super important. But yeah, like this base part here is on your formula sheet. So if you can just memorize how to get all of these from that, you will be absolutely good to go. The next super important thing for trig is just knowing your exact ratios. These triangles are on your formula sheet. This is a direct snip from the formula sheet. So don't bother memorizing these. Just knowing that they exist on your formula sheet and that you have to use them when the question says exact value. That's all you really need to know about these. Okay, don't bother memorizing this because any single one of these you can find on the two triangles they give you on your formula sheet. And it's the sort of thing that by the end of year 12, you guys will be so familiar with these ratios that like you won't even have to look at them on the formula sheet. Like you will just know that like, I don't know, the sine of 45 is 1 on root 2. You just get so familiar with them. So yeah, that's all you really need to be able to do with the exact ratios is use them to find the exact value. Okay, moving on to some of our trig rules. We've got the sine rule, which allows us to find unknown length and angles in non-right angle triangles. So essentially what we're saying is that lowercase a, which is a side, over the sine of a, which is an angle, is equal to the side b over the angle b, which is equal to the sine of c over the angle sine c. Okay, so our little ones are our sides, our uppercase are our angles. We're just saying that all of these have the exact same ratio in non-right angle triangles. So you use the sine rule to find a side if you're given one side and two angles, or to find an angle if you've been given two sides and one angle. Okay, so to use sine, you do need 3 pieces of information, and 2 of them have to be like the same thing, so like 2 sides, 1 angle, or 2 angles, 1 side. Okay, and that's how you use your sine rule. Again, on your formula sheet, so don't stress about remembering it. Then we've got cosine rule, which is looking at sides and angles, again, of your non-right angle triangle. It is on your formula sheet, so do not stress about remembering it. But essentially, you're using cosine rule to find one side, given that you have 2 sides and 1 angle, or an angle if you've been given all 3 sides. Again, on your formula sheet, so just remembering that this is when you want to use it. When you are looking at between, do I want to use sine rule and cosine rule, just think about the information that you get given, because say with sine, if you only have one side, you can't find the other 2, but with this one, if you've given 2 sides, you can find the other one. Okay, so just remembering what's in these little like red boxes will get you through using sine and cosine in your exams, like the rules. And then the other new trig like formula, I guess, that's also on your formula sheet is how to find the area of non-right angle triangles, which is just using this formula. So half times A times B times the sine of C. So when you're doing this, just remember you're using the two sides that enclose whatever angle you've been given. On your formula sheet, so not too much stress about that, but just important to know that it exists and that you can use it when you're looking at non-right angle triangles and their area. Okay, so probably one of the biggest things you get introduced to in year 11 is radians. They're just like another unit of measurement for angles. Super important that you know this. So if you guys can write this down somewhere, like it'd be super important. And so essentially what these are is how you can convert between radians and degrees. So 1 radian is equal to 180 on pi degrees. And then 1 degrees is equal to pi on 180 radians. So you guys probably, if you've done trig already at school, you would have been introduced to the fact that your calculator has a radians mode on it, which by the time you get to year 11, year 12, you do most of your trig in radians, so you do have to get pretty familiar with it. But I would say like my number one piece of advice is just to be super, super conscious of when you put your calculator into radians, because you do have to remember to take it out of radians when you're done. Otherwise, it's going to mess up a lot of your maths. So, like you can write down all the right formulas on your page and on your exam and have it all right, but the second you put in your calculator, all of a sudden you're going to get the wrong answer if you've forgotten to take your calculator out of radians. So yeah, this is essentially how you want to convert between radians and degrees. So yeah, I guess that's about it for radians. As long as you guys can remember this, you'll be able to easily convert between them. Like a lot of people find it but much easier to do the trigonometry in degrees and then just convert it to radians at the end, if that's what if your question asks to do it in radians. So if that's you, like by all means, you can do that, as long as you remember at the end to convert it into radians if your question specified that it wants your answer in radians. Okay, so another formula that you get introduced to is to find the length of an arc. And essentially the length of an arc, which is denoted by this like fancy L, is just equal to the radius times theta radians. Okay, super important that your theta here is in radians. If you don't have it in radians, you need to convert it to radians if you want to use this formula to find the length. Similarly, same situation with the area of a sector. You've got half radius squared times theta, where theta is in radians. Okay, these are just two simple formulas that you guys need to remember. I actually think they may be on your formula sheet, but I don't quite remember, but I think they are. But yeah, just want to be remembering these two formulas if you want to find the length of an arc or the area of a sector of a circle. Okay, and then the other super important thing to remember when we're looking at trig is, especially when you're looking at solving trig functions, is these 4 quadrants. Okay, so you've got A, S, T, and C, which most people remember as all stations to central. So essentially what this A means is that in this quadrant, all 3 of your trigonometric ratios are positive. Okay, in this quadrant, only the sine ratio is going to be positive. In this quadrant, only tan is going to be positive. And in this quadrant, only cos is going to be positive. So essentially, this first quadrant is 0 to 90 degrees, or 0 to pi on 2. Then the second quadrant is pi on 2 to pi, or 90 to 180. Then third quadrant is pi to 3 pi on 2, or 180 to 270. And then your fourth quadrant is 3 pi on 2 to 2 pi, or 270 to 360. Okay, so when you're solving your trig functions, you need to be checking all of your quadrants if it's going to, for which your value is positive and negative. Okay. And then the last little bit, I guess, of actual content we're looking at today before we look at some exam tips is just period, amplitude, horizontal and vertical shifts when you're looking at your trig graphs. So your amplitude is your height. It is how high your graph goes up. If you haven't changed the amplitude for your sine and your cos graph, the amplitude is 1. So yeah, it's how high it goes up. How most people think about that is if you look at the total distance between the highest point and the lowest point in your graph, calculate that divided by 2, and that'll give you your amplitude. So your period is how long it takes to get a full trigonometric cycle. The most common way to think about that is 2 pi on b, where b is just this number here. Your phase shift is moving it left or right, same as if you moved any other graph left or right, you'd get plus or minus c, and then same thing with your vertical shift, up or down for d. Okay, and so if you guys can just remember these little bits and pieces for your trig and metric graphs. Super uncommon that you'd ever calculate the period with degrees because your trigonometric graphs are graphed based on radians. So this isn't super common, but if you just want to know it exists, there it is there. Okay, well, that brings us to the end of like our content for today. And now we're just going to be looking at a bit of a summary. So in terms of framing questions when you're doing a maths exam, first thing, seems super obvious, but a lot of people don't do it, is to actually like understand like what the question is going to ask. Okay, so this is us thinking about what variables exist. It's like what's changing within the question, what variable am I trying to find? Then looking at what hidden information or like assumptions are you going to have to make. So those can be assumptions like real life assumptions in a sense, where it's like assuming that if they're talking about a deck of cards, they're talking about 52 cards. Assuming that if they're talking about a dice, they're talking about a dice 1 to 6, unless they've specified otherwise. Or the other assumption that's common is like assuming information based on something you've already found. So this is common if you've got questions where it's like part A, part B, part C, to assume the information that you found in part B is correct to then use in part C. And then to also think about what is my final answer going to look like. So this is like, if you're looking at questions that have like, you'll have certain units. If you're doing like differentiation, like thinking about like, okay, there's going to be like X's in my answer. There's going to be like, this many X's, or, we're going to have a constant, or whatever it is. And the second thing you want to do is think about the relationships, formula, methods, and steps that you need to get to your final answer. Thinking about your formula sheet, what's on it, what can you use, and then again, like what methods and steps do you know, like what relationships can you derive, all sorts of things like that. Then obviously you solve. Super important to set this out right, to make sure it's super clear as to what you need to be doing, just so that whoever's marking it can really clearly see what you've done. Just in case you don't get the right answer, it's super easy for them to see like where you went wrong, and then to give you the marks for the things you did do right in the lead up to that step. But they can only do that if you've done this logically. And then the final thing you want to do is check that your answers make sense, check that your formulas have been written down right, check for miscalculations. This is what frustrates a lot of people, and I know it always frustrated me, thinking about how many marks you lose on miscalculations. Don't set yourself up for failure. Check that you've calculated things right, check that you've written the formula down right, because like accidentally writing down like a minus instead of a plus can make everything wrong. So just make sure you're checking for those little bits and pieces. And then just the last thing I want to talk to you guys about today is with your reading time, your exam tips. Okay? Use your reading time to get a look through all the questions and get a good feel for the exam. Don't use your reading time to answer the multiple choice questions. Number one, if you spend too much time thinking about those multiple choice questions, you start to overthink them, and then all of a sudden you're doubting your answers that are right, but you've just thought about it too much, so like you're getting a bit like iffy, like, oh, I don't know if this is actually right. So don't do the multiple choice in your reading time. It's fine to look through them and to see like, okay, like what am I going to have to do, but don't try and solve them. And the second reason you don't want to do your multiple choice in your reading time is because you won't be able to look through the rest of the exam if you're spending too much time on it. You want to get a feel for how hard the exam's going to be. You're going to get a feel of what questions am I going to want to spend more time on, what questions will I do less time on, things like that. Then I'd say use your calculator even for the easiest questions, okay? Because even if it's literally like 4+7, sometimes if you just got a little bit too much test stress, test anxiety, you're going to forget that 4+7 is equal to 11. And all of a sudden you're going to write 4+7 is equal to like 13, you know? So use your calculator to triple check every single question, even your easiest questions. With your time management, if you don't know a question, skip it. Not worth spending time. Not worth spending 20 minutes on a question that you don't know how to answer and losing all the marks for the questions after that you just don't get time to answer, that you actually do know the answer to, because you've spent way too much time on something that you don't know, okay? If you don't know a question, skip it, come back to it. Not worth it. I always find it super good just to write down the main points of the question again. So that's like units, measurements. If it's like questions with differentiation, rewrite what they want you to differentiate, just so you can have it like right in front of you. And then of course, show you're working out every question every time. Never ever leave like the lines blank. Always write you're working out and then your answer, just in case you get it wrong. At least whoever's marking it can see what you're trying to do and can try and give you marks. Okay, well that's actually it for today. So I'd like to thank all of you guys for coming to today's lecture. I hope you all enjoyed it, got a lot from it. If you've got any questions and you're watching this live, lingering in your head, please feel free to chuck them in the chat. But yeah, otherwise this recording will be available to you guys as well as these slides if you want to have a look back at anything. So yeah. Good luck for the rest of year 11 and year 12. You guys will all do great. And yeah, thank you guys so much for coming today.